am Mr. True. In this video, we're going to be talking about something extremely exciting and extremely important. That is the fundamental theorem of calculus. There's actually two. That's how cool calculus is. We are only going to be talking about the first fundamental theorem of calculus in this video. Not only are you going to be excited about this concept because, if you're loving calculus and you are excited about, being introduced to this majorly important theorem, but you're also going to be excited because, well, this is now going to be like our area or steps in when we are finding derivatives. We use we did a lot of problems using the definition of derivative, and we saw that was a long and tedious process, but we did it to really really nail in the idea that it was just basically a derivative is just basically a new function that will help you find the slope, the instantaneous slope of a curved line. And then we streamline the process with like chain rule and product rule and so on. Well, we're now going to do that with integration and specifically definite integrals. With the fundamental theorem of calculus, we're not going to have to go through the limit of sums process or the Riemann sums process to find those definite integrals, which of course is extremely exciting because those are long and tedious, and if you make a mistake you might not notice it for many, many lines of work. So let's get to it. We have been introduced to two major branches of calculus now in our beginning studies of calculus. First is differential, which we first got exposed to and started to learn when finding the slope of a tangent line, and the integral branch of calculus, which we first were exposed to and started to learn when finding the area of a plane region, bound by a function and an axis on a closed interval. Now, in its most fundamental, simplest ideas, slope is rise over run, or change in y over change of x, and we see that that's basically a function of division. Area, well, if you think of area, we used rectangular shapes in our studies of developing those partitions within that closed interval of a function and an axis. Area is basically length times width of all of those individual rectangles, which we then added together, and we let the number of those rectangles go to infinity with the limit of sums process and so on and so on. But we can see in its most core idea that it's just length times width. So slope is kind of like a division math operation, and area is that multiplication. We know division and multiplication are inverse math operations. Well, and of course I've got this in a very simplified notation here. We're not going to do like a proof here or talk about real theory, but in its most element concept, finding the derivative and finding integrals are inverse math operations. So these are fundamental inverse math operations, the derivative and finding the integral, and the fundamental theorem of calculus states this, and it also brings together the ideas of finding an indefinite integral and a definite integral or integration, brings those together. And so now we'll see why we started off this chapter finding indefinite integrals or family of functions which represented the antiderivative, and then while we went into limit of sums and Riemann sum and finding this area of a bound region and ultimately getting to that notation of a definite integration notation. Well, this is what it's going to say. If a function f is continuous on a closed interval ab and capital F, now let's not forget from our definitions, lowercase f is, for the integration problems, the initial function that we're given, but it's sort of like that, kind of like a first derivative type thing. And, well, not have to be a first derivative, but it's a function, and then we're going to integrate that function to see that capital F. So this capital F is an antiderivative of f on the interval, closed interval ab. So it's kind of like if I gave you a function of, let's see if I can do this verbally, 2x cubed plus 3, okay? And we found the derivative of that. Well, I said 2x cubed, so the derivative of 2x cubed would be 6x squared, and the constant would go away. Well, that initial, that first function in derivatives was the capital F, and then we took a derivative, and it would be like finding the lowercase f. Well, and we've used this notation. I'm just trying to remind you that now that we're doing integration, we're given the lowercase f. That would have kind of been like our derivative, and then we're going to find the antiderivative. The function, when we take the derivative of that function, when we take the derivative of capital F, we get lowercase f, okay? So capital F is an antiderivative on that same closed interval. then the definite integral of f of x dx from a to b, and again, this doesn't have to give us area, but we can use it and apply it to finding area. Just remember, you can't have an area that's negative, is equal to capital F of b minus capital F of a. So we're going to find the antiderivative of f, and then once we find the antiderivative of f, we're going to plug in b, this upper limit, plug in a, the lower limit, and subtract. No need to work out that long limit of sums process, or the Riemann sums process, to evaluate a definite integral if we can find the antiderivative. If we can't, then we are going to be stuck doing that limit of sums process. The definite integral of f of x dx from a to b is equal to capital F of x, and now with a straight bracket, upper limit and lower limit. This is just sort of like nice convenient notation that you can use to keep track of what you're doing in your work, and then ultimately, again, plug in the b and the a and subtract into that antiderivative. Okay, well, if you do remember indefinite integration and finding those families of functions that when we take the derivative of them, we get lowercase f, you remember that we had to do the plus c at the end, the constant, because the derivative of a constant is 0. So when we do the antiderivative, we don't really know if and or what that original constant was unless we were given some other information to find it. So why am I not writing c in this statement or in this statement? Well, I'm going to do it in general terms here. The antiderivative of, or the definite, the definite integral of f of x dx from a to b is equal to f of x plus c. I'm going to go ahead and put that c in there with that, and it's capital F, of course, with the upper and lower limit. Now, if I apply the fundamental theorem of calculus here, then I'm going to plug in b into the antiderivative. I'm going to plug in a into the antiderivative and then subtract. Well, because I'm subtracting, I have to be careful with my parentheses. So it's plug b into my antiderivative, plug a into my antiderivative with those parentheses, because I got two terms. That's going to force me, of course, or I will need to take the negative between there, that subtraction that's here, and distribute it through the second parentheses. Now when I do that, I'm going to have a positive c here from the first binomial. I'm going to have a negative c from the second binomial, and those constants are going to cancel out, and that's always going to be the case. So we have not forgotten about the c, and we just don't need to write it with the fundamental theorem of calculus because it is always going to cancel out. So there is your introduction to the fundamental theorem of calculus. I've got 4 examples, each one going from I don't know if they're necessarily increasingly in difficulty, but they're certainly all different types of problems. We're going to have one here, just if you know, entice you to keep watching. We've got a regular trinomial, we've got a fraction we'll have to break up, and it's got a radical in it. We have absolute values and a trig function. So let's get to it. Bam! First example. We have the definite integral of 2x squared plus 4x plus 1 dx from 1 to 4. We're going to find that antiderivative now. Doing a lot of properties at once, but we're going to focus on that power rule, the power rule for integration, as we go through this for each of these individual terms. So don't forget, we're going to take that exponent, we're going to increase it by 1 and then divide by that. So 2 plus 1 is 3, so we're going to have 2x to the third divided by 3. Plus, same thing with here, the second term, 4x, we're going to raise that by 1, which is 2, and then divide by 2, again applying that basic power rule of integration, plus x. And now that we found the antiderivative, minus the c there that we talked about, we're going to put a square bracket for convenience and put the values that we need to now plug into our antiderivative. So we're going to plug the 4 in and get 2 times 4 cubed over 3 plus 4 times 4 squared over 2. I could just do 4 divided by 2 is equal to 2. Simplify things a little bit. And then plus x, or that 4 that we're plugging in. So that is our antiderivative with the 4 plugged in, minus, now let's put in the 1. We have 2 thirds times 1 cubed plus 4 2 times 1 squared plus 1. Okay, so now I just have to be careful with my signs and making sure that I take this negative and distribute it through here. So we have 4 cubed. Now 4 cubed is 4 times 4 is 16 times another 4 is 64. So we have 2 times 64 over 3 plus 4 squared is 16, and 16 times 2 is 32 plus 4. Now I'm going to, well, let's just take our time. Minus, it's going to do a couple steps at once. 1 cubed, of course, is going to be 1, so we have 2/3, and then 1 squared again is 1, and 2 plus 1 is equal to 3, so plus 3. Okay, so in the next step I'm going to do two things. I'm going to add 32 and 4 and of course get 36, and I'm also going to distribute this negative sign, just showing you a lot of steps in case you need it. And I will need it too if I make a small mistake so I can find it. So 64 times 2 is 128 over 3 plus 36. Now this is going to be negative 2/3, and 4 minus 3, because we have to distribute that. I'll just write minus 3. Let's just distribute that negative sign. So now we have, well, 128 minus 2, because we have common denominators here, is 126. So 126 over 3, and 36 minus 3 is 33. Okay, now I want to, of course, get a final answer here that's nice and neat, so I'm going to put this over 1, multiply the numerator and denominator by 3, and get 126 minus 99 over 3. And let's see here. 126 minus, or 120 minus 90 is, what, 30? So now it's 36, and 36 minus 9 is, 36 minus 9 is 27 over 3, and that is equal to 9. And let me double check my answer, and I've made a huge mistake somewhere. What was that? Oh, I could delete this, but why? I make mistakes. 36 minus 3, I think, is positive 33. Woo! Don't do that in your work either. So 120 and 90 is 210. Now it's 216. And now 216 and 9 is 225 over 3. I didn't think that's the answer I got in my notes. And 225 divided by 3 is 75. Bam! So that was the end of your first example. You got 3 more. Let's see here. Yes, let's go. For our next example, we have the definite integral of u squared minus 3 over the square root of u du between 0 and 4, or from 0 to 4. Now, you have learned now just fairly recently how to find indefinite integrals. So let's practice those skills, and remember, of course, we don't need that whole family of antiderivatives with the fundamental theorem of calculus, doing work using it to find this definite integral. So we don't need the plus c there, remember, but find the antiderivative, plug in the 4, plug in the 0, subtract, and see what you get. As I'm going to give you the opportunity to practice those skills, let's not forget that we don't have a quotient rule for finding integrals at the moment. We just have that basic power rule, which is powerful, but it's, pretty much the most powerful integration rule that we have. So you're going to have to do some rewriting here, get this out of the fraction notation, and you also want to do something to take care of or rewrite that square root as you work out the problem. And I'll reveal the answer in 5-second increments, like I've been doing recently, to give you an opportunity to practice the problem on your own and make sure you haven't forgotten those skills you learned a few sections ago. Okay, so give this a shot. I'll reveal the answer in just about 5 seconds. Okay, so hopefully you got your 4/5. Now my examples, and all my examples, for some reason, I had come out to be positive answers. Don't forget, you can get a negative answer when finding a definite integral. Those negative answers just cannot represent area. But every time you do a definite integral, you're not necessarily just finding the area bound by a function and an axis on a closed interval. So don't worry about that if you happen to get a negative answer, unless of course the question is asking you to find area, and then something's amiss somewhere. So I took my fraction, of course, and wrote it as two separate terms, and rewrote the radical to be power of 1/2. When you divide like bases, you subtract the exponents, raise those exponents by 1, and divide it using that power rule of integration. When you divide by a fraction, it's the same as multiplying by the reciprocal, so I flipped those bottoms up, and I don't think we need the reminder now, but when we have 4 raised to the 5/2 power, it's 4 to the 5th power and the second root. So the square root of 4 is 2, and 2 to the 5th power is equal to 32, common denominators, and there's our answer. So let's get to the next one, shall we? Okay. Our third example, find the definite integral of the absolute value of x minus 3 plus 1 dx from -2 to 5. And we know that absolute value functions are going to give us a little bit of a special challenge because we have those sharp bends. And, you know, while an absolute value, what happens to those sharp bends? Why do they exist? Well, of course, we know absolute value functions will tell us how far a value is from 0, basically, on a number line. And if that number is positive, let's say 5, then the absolute value of 5 is 5. If it's -5, the absolute value of -5 is, well, -5 is, 5 units away from 0. So we want to just say absolute value functions, get rid of negative signs, because that is, mathematically or mechanically what we see, but it is telling us that distance from 0. So we effectively need to deal with this problem as two separate equations. What's happening to the left of that value and to the right of that value where the absolute value function itself is equal to 0? Because to the right of 0, if you take the absolute value of a positive number, it just stays positive and nothing really changes. To the left of 0, well, then it's going to be getting rid of those negative signs. So when I say 5, was it 5 that gave me that? Absolute value of 5 is 5, or was it -5? The absolute value of -5 that gave me the positive 5. So we need to find out where this function is equal to 0, and of course we're going to do that by setting it equal to 0 and solving that little equation. I just sort of wrote the answer because it was just, I should have wrote it out. X minus 3 is equal to 0, and the solution to that is x equals 3. So if we plug in a value that is less than 3, like 2, then 2 minus 3 is equal to -1, and the absolute value of -1 is +1, and it shifts. So this is what we're going to do to handle that. We're going to say that the absolute value of x minus 3 plus 1, and don't forget graphically, this is just, if you were graphing y equals this function, this +1 at the end here is just a vertical shift. That's not going to change what's happening inside that absolute value function, so I'm kind of ignoring the 1 there if you hadn't noticed. This is going to be equal to, well, let's see. What about when x is, again, less than 3? Then what's inside that absolute value function is going to be negative. So it's going to be negative parentheses x minus 3. I'm taking those absolute value functions out and replace them with a set of negative parentheses plus 1. So this is going to be our function when x is less than 3. Now the absolute value of 0 is 0, so nothing changes. The absolute value of anything positive stays positive, so it appears that nothing changes. So when x is equal to 3 or greater, then our function is simply going to be the x minus 3 plus 1. So we're actually going to go through the integral process of two separate functions. And it's going to look like this. This is now going to be written so that it's equal to the definite integral. Okay, so I want to integrate between -2 and 5. Well, -2 is less than 3. So when we go from -2, I'm going to kind of, keep this in the order of the number line. This is my lower bound, and I'm going to go up to this sort of, magical number of 3. So when we do the definite integral between -2 and 3, we want to do that with this function here, negative parentheses x minus 3 plus 1. And let's not forget the dx. Then that's not going to be the total area. I want to find all of the area between -2 and 5, and I've just gone between -2 and up to 3. So I need to get from 3 to 5, and I want to, well, I'm talking like we're going to be doing area. I guess it could be finding the area of this function between the function and the x-axis between the closed interval of -2 and 5, because this answer is going to come out to be positive as well, or just evaluate the definite integral. At any rate, I need to add the two parts, so whether it comes out to be a positive or negative answer, we're finding area or not, we need to add up those two parts. So now we're going to go from 3 to 5. So the definite integral from 3 to 5 of, well, if I'm using values that are going to allow the expression inside the absolute value function to be positive again, I just have x minus 3 plus 1, which of course is just x minus 2. I am going to write it all out though, because I'm teaching you guys what's going on. So x minus 3 plus 1 dx. Now, I'm going to step off and give you a chance to work this out on your own, to practice these new skills of using the fundamental theorem of calculus and bring out the answer one step at a time, and allow you to try it on your own and hopefully get the right answer as well. Let's see what happens. All right, I hope you got it. As I look through my work here, anything I want to point out with you, is just very, very careful use of parentheses. Again, these are long problems. I'm showing my steps, not just so many steps, not just to help you understand what I'm doing, but help me as I was going through this, even though I was quietly writing the workout and pausing the video, of course, to let you try it and just reveal the answer. I made a sign mistake as well and had to go back and fix it. So it was a small one, but still a small mistake like a sign error gives you the wrong answer. So be careful and go slowly and carefully, and thoroughly write your work out. Okay, so what I mean is here, like this negative x squared, make sure when you plug in the 3, or especially like this -2, that you don't just take those two negatives and multiply them together and make a positive number, because you do have to do exponents before you multiply, of course. Well, that was not the sign here that I made before, I just miscopied it. And as I simplify from this line to this line, you'll notice that in some of these numerical values I did not include any parentheses, and some of them I did. Of course, I included those parentheses after the subtraction sign, because inside here I have two terms, and I can either, of course, make those two terms 1 since it's all arithmetic, but I saw all of those common denominators, and I just wanted to, that's whatever. It's how I showed the work. So I want to take that negative that's in front of the parentheses and make sure that it distributes, and I don't make that sign error in the second term that's in those parentheses. Now, if you made all these single numbers, then maybe you would have your work looking a little different and not have to be so careful about these parentheses after those negative signs, because they do need to carry through. So ultimately, though, the answer is 43/2. So with those questions that involve absolute value functions, you are going to take what's inside the absolute value, set it equal to 0. That's going to be your break, where you are going to sort of make your going to make your piecewise function and have the set of negative parentheses for those values of x or u or whatever variable that you have here in your problem that come out to be negative inside the absolute value function, and of course have another equation for the positive answers. Let's get to our last example for this video. Here's our last example. Change the wording a little bit. It's not going to change the process of the problem, because one application of definite integrals is finding areas bound by a function in an x-axis or y-axis. And I have a problem here with it's a fairly straightforward problem, but still one with a trig function, and to remind you that you need to remember how to integrate all those integration formulas for your trigonometric functions. So we're going to determine the area of the region bound by the function f of x or y is equal to 2 cosine x, and the x-axis on the closed interval of negative pi over 2 to positive pi over 2. So I've given us a sketch, and I have the shaded area that we're interested in. And we want to remember that when we're doing indefinite integrals, the integral, or the integral of cosine x dx is equal to the sine x plus c. So if that were not off the top of your head, I don't know what your teachers are requiring for your class. Maybe you have a formula sheet. More than likely, though, you're being asked to memorize these. So do what's appropriate for your studies. Okay, so I want to write this area is going to be equal to the definite integral from negative pi over 2 to positive pi over 2 of 2 cosine x, and don't forget, what are you integrating with respect to? So don't forget the dx. So that's going to be equal to 2, well, let's show all the steps, just because it's a trig function. One of the properties of integration says we can take this constant and move it out front. So this is equal to 2 times the definite integral of negative pi over 2 from negative pi over 2 to positive pi over 2 of cosine x dx. It's really important with those integration formulas that you get your problem exactly in the same format as those integration formulas before you try and apply them. So it's good practice to go ahead and take that 2 out. Even though we may be comfortable with it, you don't want to shortcut that process, especially with the trigonometric functions. So again, the integral of cosine of x is sine x plus c. We don't need the plus c with the fundamental theorem of calculus, though. So we're going to have 2 times, let's see here, sine x with the upper bound of pi over 2 and lower bound of negative pi over 2. So we just need to merely plug these into our antiderivative and work out the problem. So we have 2 times, plug in your pi over 2, so we have the sine of pi over 2 minus the sine of negative pi over 2. Don't forget that unit circle either, because it's really going to bog you down and slow you down if you have to really work at trying to figure out what these values are, those 16 angle values that are on the unit circle. The sine of pi over 2, remembering that sine is y over r, and that's 90 degrees on the unit circle, so the sine of pi over 2 is equal to 1. The sine of negative pi over 2, that's a negative rotation, so the sine of negative pi over 2 is negative 1, so minus a negative 1 that we're getting from our sine function. Of course, 1 minus negative 1 is plus, or 1 plus 1 is 2, so we have 2 times 2, which is equal to 4. And let's go ahead and put that unit squared on it, because we are finding an area. And the units of measure for area is units squared. So that's your introduction to the fundamental theorem of calculus. Very, very cool. Streamlining that definite integration process. I'm Mr. True. Go do your homework.